Assalamualaikum warahmatullahi wabarakatuh. So we are from group 2. We present about tree and sorting for our assignment 2 in CSC508 data structure and algorithm. So let's begin. So first of all, let me introduce myself. My name is Danish Imran and this is my fellow members Alif Shazwan, Daniel Mikael, Ali Imran and Nadrul Shahmi. So first thing first, what is a binary tree? So let's begin. A tree is a recursive and a non-linear data structure used to represent data organized hierarchically. It consists of a collection of elements called nodes which are linked into their successor via branch. So this could be the example of a tree. It's made up of nodes and edges. Nodes can be some pieces of a data. So the top of the tree is called a root nodes, and then the bottom of the tree is called a leaf node. So what is root node? So the root node basically is a node that have only outgoing edges but no ingoing edges. And then same to the leaf nodes. The leaf node is the nodes that only have ingoing edges but no outgoing edges. Then next, so a nodes that doesn't have any ingoing edges is also called a parent nodes. And then nodes that only have outgoing edges and no ingoing edges is called a child nodes. And then a parent and a children can be both, because some nodes have ingoing and outgoing edges. So the next, so if two children that share the same parents, we call that siblings. So a siblings is basically a nodes that share the same parents. So what is the level in the tree? So the level is the number of a branch on the path from the root to the node. So let's see here. So the level of the root node is 0. So this is the root node and the level is 0. And then the level of the children of the root node is 1. And then we see here, the level of the children of the root node is 1. So next, what is height? The length of the path from the root to the deepest node in the tree, as we can see here. So the length of the path is 2. So the height of this tree is 2. And then what is subtrees? So a subtree is a tree is often divided into the sets of nodes called the left subtree, we label it as LT, and the right subtree, we label it as a RT. Next, so there are 3 types of tree in here. So the first is the binary tree, the second one is binary search tree, and the last one is the AVL tree. So what is a binary tree? So as shown here, each node has no more than 2 children. So the least node is 1 and the max of node is 2 here. So what is full binary tree? A tree where every node has either 0 or 2 children. So as we can see here, if 4 and 5 and 6 doesn't have here, so 1, 2, 3 is a full binary tree. And then if 1, 2, 3, 4, 5, 6 and also have 7 here, it also a full binary tree. So what is perfect binary tree? A perfect binary tree is a full binary tree in which all leaves are the same depth. So it means like from the left subtree and the right subtree has the same depth. So it is called a perfect binary tree. So this is the example for the binary search tree. So the value arranged in the certain order is the root node is bigger than the left child, and the root node is smaller than the right child. So both the left and the right subtrees must also be a binary search tree to become a binary search tree. So the last tree here is the AVL tree. So what is AVL tree? AVL tree a self-balancing binary search tree. If an insertion violates the balance criteria, the tree is reconstructed using a rotation, which is left rotation, right rotation, or double rotation to restore the balance for the tree. And then I will show you what is the rotation in the AVL tree. So here is the example for the right rotation, which is the first node we see here is a left unbalanced tree. So we need to do a right rotation here to balance the tree. So the node C, which is the unbalanced points, move down to become the right child of its original left child, the node B. And then node B move up to become the new root for the subtree. So now the tree is balanced. The right rotation is same like the left rotation like here, because when the right unbalanced tree here as shown here, the node C, the unbalanced points, move down to become the left child of its original right child for the node B. As we show here, the node B move up to become the new root of the subtree.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rizal bin Mustaqim, and I will explain to you guys the operations involved in a binary tree. There are 5 operations now, so let's go through one by one. First, we have insertion. Insertion is the process of inserting a node in our binary tree. So the fundamentals that you guys need to understand is, if the value of our inserted node is more than our current node, we move to the right subtree, and if the value of our inserted node is less than or smaller than our current node, then we move to the left subtree. So let's take a look at an example. Let's say we want to insert 10 in this binary tree. So how will it happen? So first we have a node 10, and first it will compare with the root, which is 16, and 10 is less than 16, so it will move to the left subtree, and then it will move to 7, the next node. Then 7 and then 10 is more than 7, so it will move to the right subtree, as you can see here. So this is how insertion works. And however, you guys need to remember that in an AVL tree, rotation process must be done if the insertion violated the balance criteria. So the next is deletion. Before we go deeper, you guys need to understand the fundamentals. Successor or and predecessor. Successor and predecessor is used when we want to remove the root of a binary tree. So what is successor? Successor is the leftmost element in the right subtree. So in this tree, the right subtree and the leftmost element is 19. While the predecessor is in the left subtree, the rightmost element is 10. So 10 is our predecessor. So let's try to remove a node. So let's say we want to delete 19. So as 19 is at the highest level in our binary tree, so we just can simply remove it like this. So this is our new tree after we delete 19. So the second case is when we want to delete 7 from this tree. However, 7 is the parent of the 5 node, and 5 is the child node of 7. However, if we delete 7, 5 and 2 will be left hanging. So how to do it? First, we remove 7 and we put 5 to hold to upper level, and same goes to 2. It will be replace the position of 5. And the third case is when we want to delete 16 or the root. So in this case, I choose to use the successor. So if we remove 16 or the root, 19 will replace the position of the root, and it will go to the top, and 19 will be removed. This is the case where the successor is used to replace the root in deleting the root. So the next is searching. So how to do searching in a binary tree? Same as insertion, the fundamentals used are the same. If the value is less or smaller, we go to the left, and if the value are bigger, we go to the right. First, we need to compare the value with the node at the current iteration, and repeat the process for several iterations until we found the node that we want to search. If we don't found it, then it will return to false. And if we found it, it will return to true. So let's say in this tree, we want to search the number 21. Let's go. Let's see how it goes. First, 21 will compare with the root, which is 16. As 21 is more than 16, it will go to the right. And 21 is less than 23, it will go to the left. And 21 is more than 19, it will go to the right. And you found it. This is where 21 placed in this tree. And next is the height. Height is the maximum depth or height of the tree is from the root to the deepest node. If you look closely in this tree, the left subtree have 3 levels. However, the right subtree only have 2. Even the right subtree only have 2. The height of this binary tree is still 3. We select the deepest level that you can reach from this binary tree. So in this tree, the height is 3. And lastly, traversals. Traversals is we will visit every node. However, there are 3 ways to do traversals: in order, pre-order, and post-order. So let's go through one by one. First, we have in order. In order, first you must go all the way to the left subtree, to the node, and all the way to the right subtree. So let's say in this tree, the in order traversals is first we go to the left subtree, which is 1. The leftmost subtree is 1. Then we go to the 5, 7, back to the node 16, and then until that we finish the right subtree. However, we did not go to the 23 as the stages left subtree. So we go to the 19 node right subtree. So do you guys understand? Next, we go to it's also in an AVL tree. In order also was arranged by ascending order. Next, we have pre-order. Pre-order is the top from top of the tree to down, top down. So first we go to the node, which is 16, the root, which is 16. Then we go all the way to the bottom. So here we have 16, 7, 1, and 5. We finish all on the left side of the subtree, and then we go to the right subtree. 16, 7, 1, and 5. And then we go to the node first, 23, left and right. 23, 19, 31. As you can see here, it is the same. And lastly, we have post order. Post order is where we choose to visit the root lastly. So first we finish the left, we go to the right and node. So here we have 5. We finish the left subtree 5, 1, 7, and then we go to the right subtree. However, we start from the left first. Left, right, node. 19, 31, 23. Lastly, we go to the root 16. So that's how you do the three types of traversals. I'm sorry. Okay, that's all from me. Thank you.
Assalamualaikum, my name is Al Imran and I will explain about the performance in tree algorithm. So let's look at the performance that can lead to poor or optimal performance. So firstly, for poor performance, a tree can become inefficient as its height increases unnecessarily. So let's look at this diagram. So in search of E, the tree height is 3. So to make it optimal or increase the search performance, we can make the height as 2 by placing the E at the bottom right of B. So because of this tree is left heavy, it will degrade the search performance. Okay, next, to reach optimal performance, so we must make or have a perfectly balanced binary tree. So in a perfectly balanced binary tree, the height of left and right subtrees are equal and all leaves are at the same depth. Okay, so let's look at the diagram here. So in the diagram, all the leaves are at the same depth. So to ensure that the shortest possible path to any node. Okay, let's look at the ways to achieve the most efficient binary tree. So firstly, balance
is equal to speed. So the more balanced the tree or closer to a perfect binary tree, the better the performance. And next, AVL tree are the performance solution. So like my group member presented before, they use rotation to prevent the tree from becoming skewed and inefficient. And lastly, what affect the efficiency of binary tree is the height factor. So we always have to aim for the minimum possible height for a given number of nodes to ensure the fastest data access.
And a very good morning. My name is Denis Mikael, and I'll be explaining about the real life applications of trees in society, basically. So the first one are file systems. Now, for file systems, they use folders and subfolders, and these can be represented as a tree structure. Now, for the example I've given on the side here, the C drive in any normal computer would consider it as the root node. And from those root nodes, or the C drive, you have users, program files, and Windows as the folders. It will be a subfolder to the C drive. And in those would be considered the first layer of nodes. Now, in users, there's also Daniel and public. Those would be the nodes from the user node. And same goes for how Google and Microsoft for program files, and so on and so forth. And one thing to note is that for file systems, this is considered a binary tree because, unlike a binary search tree, it has more than two nodes for a single node. Next are the databases. So for databases, these are used for quick searching, inserting and deleting for records. And usually they are faster than linear search. Now, databases, for this example, are like for patient records. Now, why is it considered a BST, or how it's using BST? For each node, it is used to represent a patient ID. So the reason why most databases use this tree structure is because it is simply a lot faster than how you would use another tree, like say the binary tree. And this is very crucial in the medical field because of how emergencies tend to happen, and you would need to look up medical records in a short amount of time. Now, next are decision trees. Now, these are for logic purposes. So let's say in this case, a medical diagnosis system, it would ask a question. So let's say ask if the person has a fever, that person that person does have a fever, and then they will ask if that person also has a dry cough. And if both are true, then that person has COVID. But let's say the dry cough is not true, then the person has a flu. Now, that is usually these are used for systems that require a lot of questioning, like the example I've given. Next, I will be talking about some past year questions. Now, for the first one, the question A states, state the three traversals in a binary search tree. Now, for question A, the three standard depth first traversals are in order traversal, pre-order traversal, and post-order traversal. Now for question B1 is given the following list of numbers. Draw the binary search tree, which I have done on the side here. Now for question B2, it says to write a recursive method to display the elements in a binary search tree ascendingly. Now this is the code that I've written. One thing to note is that because it is recursive, you would do a while loop using a sentinel controlled. Now, next question C. For question C, insert the following sequence of following numbers, or sorry, the elements into an AVL tree. And I have done that step by step. One thing to note is that the ones that have two images are the ones with rotations. As you can see for number 3, for Huawei, Samsung, and Sony, you can see that So Samsung is rotated to become the new root node. For number 5 is when Apple is introduced, and Apple is rotated to be the new node for replacing Huawei. And for number 6, when Alka is introduced, uh, Huawei is rotated back so that Samsung becomes a new root for Nokia and Sony. And for the other rotations are number 9, when Oppo is introduced, completely changing OnePlus to be a new root node. And lastly, when Lenovo is introduced, it completely shifts everything so that OnePlus becomes the top node. Now that's for the questions that I've done. I will pass it to the next presenter to continue on the other past few questions.
Thank you. Assalamualaikum and a wonderful day to Madam Anis. My name is Muhammad Nazul Shami bin Nizam and I will be continuing by presenting my part of the presentation. So another partial question I would like to share today is shown on the slide. Question 3 from July 2024. A binary tree is a hierarchical structure composed of nodes where each node has at most 2 children. Given the following binary tree, identify the sequence of nodes visited based on in-order traversals. We will now answer this question. To solve the sequence of nodes visited within in-order traversals, we must start with the rule, which is to visit nodes in the following order from left to right subtrees. Starting from A, we go to the leftmost node, which is lower than C, which is M. So M is our first visited node. Then we visit the root of the subtree, which is C, and visit the right child, which is A. With this so far, our node path is M, C, and A. After completing the left-hand side of the tree, our next inline for the node path that makes up MCAA. Now looking at the right-hand side of the subtree, we visit R followed by O because this is the only path available that makes our current path MCAARO. From O, as the root, we have 2 children, O and S. Following the rule, we head to the left to find out next node path. Because O only has 1 child and the child is on the right side, N is taken on the next node path followed by its root O. That makes the current path MCAARONO. Finally, the last visited node will be S. This makes the final answer for this question MCAARONOS. Moving to the next question. A2. The following figures show 2 types of binary tree. Identify and describe both types of binary trees. For binary tree A is a full binary tree because the lower level of both subtrees both have 2 children. The answer for binary tree B is complete binary tree because on the last level of the tree there is only 1 subtree with 2 children. Meanwhile, the right hand side does not. Moving on to question A3. Based on the following binary search tree BST, draw the updated BST after node 76 is removed and node 37 is added. First, we replace the original root 76 with the highest of its 2 children, which is 86, and the rest of the subtree is also pushed upwards. Next, we add 37 starting from the new root 86 because it's smaller than 86, but 18 because it's smaller than 86, and 30 but bigger than 18. 45 become its new root and placed as the left child on subtree root 45. Moving on to question B. An AVL tree will be created based on the following list of flowers: lily, rose, tulip, daisy, freesia. Show the step-by-step process of creating the AVL tree. Indicate the balance factor of each node. Okay, so we start answering this question by starting from the left of the list to insert into our AVL tree. Step 1. Lily becomes the base root of the tree and is completely balanced. Step 2. We add rows. We add rows. Alphabetically, R is after L, so that makes R bigger than L, so it's inserted on the right side. Step 3. We add tulip. Tulip is bigger than lily and rose, so it goes to the lowest level of the tree underneath rose. This will cause the tree to be unbalanced, so a rotation is done at lily to balance the tree out. Step 4. Adding daisy. Step 4. Adding daisy, which is the smallest out of all so far, so it was inserted on the far left below lily. Step 5. We insert freesia under daisy and do a left rotation at daisy. After that, another rotation at lily to finalize the balancing so far. So our finalized answer for this AVL tree is shown in the slide.
So now we have reached for the second part for our group presentation, and then this is the sorting topic. So first of all, what is sorting? So sorting is an algorithm that the method for reorganizing the large number of items into a specific order, such as ascending or descending numerical order or alphabetical order. So the definition and the purpose of sorting. So the first one is the selection sort. So what is a selection sort? So a selection sort is an algorithm that repeatedly finds the smallest element in the unsorted portion of a list and move into a beginning by swapping it with the element currently in that position. So if we have a straight line, we are going to swap the first and the second element in position if the element is more smaller than the second element. So the purpose of this selection sort is to sort a list by a progressively building sorted section. So it focuses on the selecting the correct element for each position one by one. So the example will be shown by my friend, which is Alif Shazwan. And the second one is insertion sort. So what is insertion sort? So it is an algorithm that builds a sorted list on one item at a time by finding the first unsorted element and moving it to its proper position. So the purpose of this insertion sort is to reduce the number of key comparison compared to the selection sort. So for the third one is a merge sort. So merge sort is also called a divide and a conquer. Why? Because it recursively sort them and then merge the sorted sublist into the one final sort list. Like we have 8 element in one straight line, we will divide it to a 4 and 4, and then we will divide it to 2, and then we will merge it again after we have swapped the position for the smaller to the biggest element. And the purpose of the merge sort is to sort the large list efficiently by breaking the problem down into the smaller sublist. Then this also will be shown by my friend Ali Shazwan. And for the last is the heap sort. So what is heap sort? Heap sort is a comparison-based sorting technique that utilizes a binary heap data structure. A heap is a complete binary tree where every parent node is compared to its children. And the purpose of this sort is to the sort elements efficiently. So typically, it increasing order by building a max heap to find the largest item. So now Ali Shazwan will explain more about how we are doing the sort.
Hello, my name is Muhammad Sultan bin Mustaqim, and today I will explain to you guys the type of sorting algorithms and how to do it. So let's go. The first is insertion. How to do insertion? We will basically we will split it into two groups, sorted and unsorted. And the instruction are here. First, we start with the second place, and we compare it with the first. And if it's smaller, swap. So we move to the next and repeat step 2 again and repeat it until done. So let's see how to do it. So let's say I have an example of an array here. It has the number 3, 2, 8, 1, and 5. So how to do it? So we start with the second place, which is 2, and we compare it with the first, number 3. As 2 is smaller than 3, we swap it. And now, this become the sorted part, and this become the unsorted part. So the second step, this is after we swap it, we go to the next, which is 8. So 8, the same process. we compare it with the first portion of the unsorted part. So if it does it smaller? No. So it has been already sorted. So this become our sorted part, this become our unsorted part. Next, we go to the next, which is the number 1. So we compare it with the first. So as you can see, 1 is smaller than 8, it is smaller than 3, and it is also smaller than 2. So we move it to the back until you didn't get anything that's smaller than it. So we swap it 3 times here. And this become the sorted part, and this become the unsorted part. This is where we already swap it. Now we go to the next, which is 5. So we repeat the same steps again. So as you can see here, 5 is smaller than 8. So we swap it. And after you swap it, you have done it. This is the sorted part, and this is the unsorted part. And this is the array after we swap and sorted it. So that's insertion. Next, we go to the selection. So how to do selection? First, we find the minimum and the current, and then compare. If it is smaller, then we swap, and we repeat it at the unsorted portion. So let's say I have another example of an array here. We have the number 5, 3, 8, 2, 1. So first we need to find where is our current. So we are currently at the first array, which is 5, and we find where is the minimum current. So we have the number 1. 1 is our minimum. Does 1 smaller than 5? And the answer is yes. So we swap it. And now this became our new array. 1 is at the places of 5, and 5 is at the places of 1. And then we repeat the same step at the unsorted portion. This become our sorted portion, and this become our unsorted portion. So next, our current number is 3, and our minimum number is 2. And 2 and 3 is smaller than 2. So we swap it again. And this is our new array after we swap it. This become the sorted portion, and this become the unsorted portion. So our current number 1 is 8. So we find the minimum, which is 3. We do it again. We swap it because 8 is small. 3 is smaller than 8. So we repeat the same steps, and this became our sorted portion, and this became our unsorted portion. And lastly, we are currently at number 8, and 5 is smaller than 8, and we swap it again. So finally, this is our sorted array: 1, 2, 3, 5, and 8. And this is sorted portion, and it is completely sorted. So next type is merge. Beforehand, you need to understand three fundamentals of merge. We have divide, where we divide into 2 halves until it becomes a single array. Next, you conquer, where you sub-array are sorted individually, the sub-array that we have been dividing, and merge, where the sub-array are merged back in order. So let's say I have an uneven number of array here. We have 5 number of element. So first we divide it into 2 halves. One part having 2 element and one part having 3 element. It was easier if you have even number of elements, but I want to show a harder example. So we split it into 2. The first part having 3 and 2. The first part having 2 elements, and the second part having 3 elements. We split it by 2 again until it became single elements. 3 and 2, we split it by half, become single now. And 8, 1, however, it doesn't become single, so we need to split it again. And yeah, it become like this: 3 and 2, 8, 1, and 5 all become single element. So after that, we do conquer and merge. So this is our divided array, where 3, 2, 8, 1, and 5 have become single. While merging, you need to sort it. While merging, you need to sort it. As you can see, 2 become at the front because 2 is smaller than 3. This is where the sorting happens. The same happen here, where 1 is smaller than 8, so it become the first, and 5 doesn't merge, so it can wait. So we need to do again until we get the original array. So 2 and 3 are already sorted, so nothing changes. However, here, while merging, 1, 5, and 8 are sorted, where 5 was smaller than 8 and it came before it. So here, we sorted totally, where 1, 2, 3, 5, and 8 were sorted according to their number. This is where the conquer and merge happen. So this is the merge sorting. So now you are done. And lastly, we have heap sort. How to do heap sort? First, we treat as a binary tree, and then we find the max heap and we sort the array by swapping the largest with the smallest end of our binary tree. So first, there are several things that you guys need to understand. First, how to convert from an array to a binary tree. Let's say I have an example of array which is 5, 3, 2, 1, 6, 9, and 8. So how to convert it to binary tree? So we read it from left to right, and we sort it by levels. So the first level or the root, we have 5, and then from left to right, 5, 3, 2, 3, 2, 5, 3, 2, and we continue it at the third level, 1, 6, 9, 8, 1, 6, 9, 8, 5, 3, 2, 1, 6, 9, 8, and there we have done our binary tree from our array. Next, you need to understand what is max heap. Max heap is the root where the root is the highest value. As you can see, the highest value in our tree is 9. So 9 should be up there at the root. So that is max heap. So let's see how to do max heap. So how to do max heap? This is our binary tree or our array without converting it to max heap. So first you need to understand what is the parent node and what is the children node. Let's say my parent node is 2. So what is my children node? So my children node is 6 and 8. So another example, if my parent node is 5, then my children node is 3 and 2. So next step, we need to make sure the parent node is the largest, and if not, we swap with the biggest children. So let's say at the left subtree, we start with the bottom or the left subtree. 3 is our parent node, however, the biggest children is 9. So we swap it. And then we continue with the right subtree. 2 is the parent, however, the children are bigger than it. So we swap it, where the largest children is 8. So we swap the place, and then we continue it for the upper level. Here, 5 is the parent node, however, 9 is the bigger children, so we swap it again. Tada, you got your max heap. And lastly, we want to know how to sort the array or the third step. So first, we need to swap the root, the last element in our array, and we need to always make sure that the max heap is not violated at all. And you guys need to remember that our array is arranged by the 3 levels. So you can see here, which one in this tree is the last element in our array. So the answer is 2, as you can see from left to right. And this is our last element in array. So let's do it. So you swap the root with the last element, which is 2, and 2, you swap it here. And then you need to always make sure that max heap is not violated. And now you can see that 9 has already successfully been sorted. However, max heap is violated here, where, as you can see, 2 as the parent node have a bigger children, which is 8. So here, you've done the max heap, swap the places of the parent and the children, and now this is your new binary tree. And we continue the process where we swap the root with the last element. However, 9 has been already sorted, so we continue with 6. We swap it, then we are done. And this is your new tree. 8 and 9 has been successfully sorted. But do you see any max heap was violated here? The answer is no. So we can just continue swapping the root with the last element. Then you've done it. And this has become our new binary tree, where 6, 8, and 9 has been successfully sorted. However, max heap has been violated here. So you swap the tree with the 5 because 5 is the biggest children that 3 have. So you swap it, and then this is our new tree. Does not violate any max heap. You continue the process of swapping the root with the last element that has not been sorted, and then 5, 6, 8, and 9 has been successfully sorted. However, max heap violated again here. So you repeat the process of swapping with the biggest children. It's the same process all over again. Here you swap with the root with the last element, and here you do it again. And there you are. This is our completed binary tree where we have sorted, where we swap the root with the last element. So we need to convert it back to our array. So you guys remember we set it to the levels, and from right and from left to right, sort it 1, 2, 3, left to right, left to right. So this is our sorted array, and then there you have it. You have done heap sort. That's all from me. Thank you.
Okay, now I will be explaining about the performance in sorting algorithm. Okay, so to measure the efficiency or performance in sorting algorithm, we have to look at the time complexities, which uses cases to measure it. So there are three cases, which the first one is best case, which the data is already sorted or nearly sorted. Next, for the average case, is when the data is random, mimicking the real world order. And lastly, for the worst case, is when the data is in the worst possible order, and usually is reversed. Okay, from this table, this is the time complexity table. So first, we have to understand that there are three operations, which is the linear operation, quadratic operation, and log linear operation. So linear operation basically is when the loop is running a single pass through the element, and quadratic operation means it will run in a nested loop. And lastly, for log linear is the element is divided. So for let's look at the algorithm one by one. Okay, for insertion, when the data is in the best case, it will run the linear operation, and for the average and worst case, it will run the quadratic operation, which is the nested loop. So for next, for selection algorithm, for the best case, average case, and worst case, will all run the quadratic operation. For heap and merge, we know that they divide the element in the they will divide the element, so they will use the log linear operation. Okay, so let's look at some code snippets uh, to see more clearly. Okay, so for insertion sort, so we can see that it will run the loop one time through the element. Okay, next for the selection sort, it will to find the smallest element, it will run in a nested loop. Okay, so for heap and sort, we know that it will divide the element. So we can see at the code here, it will swap and recursively move down through the element. So next, lastly, for the merge sort, we know that it is divide and conquer. So it will split left half and split right half, and then join them back together. Okay, as a summary, firstly, insertion performs well for small or nearly sorted datasets. Next, selection are generally inefficient for large datasets because of it will run through many loops. And next, heap is suitable for memory constrained environments where an in-place sort is necessary. And lastly, merge is one of the most efficient sorting techniques.
Okay, assalamualaikum. Sorry. Okay, thank you. Now I'll continue on with some real life applications for sorting. Firstly, we have ranking lists. Now, ranking lists are very important, especially in universities, where this kind of sorting system is used to sort students by, let's say, exam marks, GPAs, or merit. These are very important for students to determine if they are eligible for scholarships or dean's list. Another example of how ranking list works, or another example, it would be how games have leaderboards and sorting players based on how good they are as a player. Next, we have transaction sorting. Now, banks and financial institutions use sorting algorithm to process and display transactions. This is important because usually transactions are very random. Now, for some examples, organizing a bank statement by date to show a chronological history, or sorting transaction by amount to identify large suspicions withdrawals. Now, this is to show if a person is spending money from their account on, we can see if they are spending every day a certain amount to catch some suspicious activity. This is usually important to determine if that person either lost their credit card or another person is using it secretly. So some of the key concepts would be sorting, helping in reconciling accounts and detecting patterns in financial data. Like I said before, this is used to detect if somebody's stolen debit card or credit card is being used by another person. Now I'll be going through some past year's questions. Now for question A, it says identify two differences between merge sort and insertion sort. Now for merging, the time complexity, if they're efficient for large data sets with consistent performance, while insert is efficient for smaller ones or nearly sorted data sets. Now for strategy, it uses a divide and conquer approach by splitting the list into halves. Meanwhile, insert uses a incremental approach by building a sorted section, one item at a time. So for question B, given the following list, show the steps to sort the given list using selection step sort in ascending order. I've done this question and it's a little long, so as you can see, the question, for thing of note is that for pass 2, it's already in the correct position, so there's nothing to change. For pass 3, 180 is swapped with 320. For pass 4, number 320 is swapped with 440. 388 for pass 5, 388 is swapped with 440. For pass 6, 398 is already in place, so not changed. Now, for question C, sort the following using a merge in descending order now. And I've done that on the side there. First, you would divide the number into halves, and then from there, you can just merge and then do the descending steps. Now, for question D, for question D, it says write a method to sort integers in an array using insertion sort. Now I have done the coding here, and as you can see, I've written the notes there. It says move elements from array 0 to 1 that are greater than key, and then to one position ahead to their current position. That is for the method below. That is all from me. I will pass it to the next presenter for the other past few questions.
Hello again, and now I will continue with another past year question. This question was taken from July 2024. Question A. Consider the following data series 21, 43, 29, 17, 65, 10, and 4. Sort the data series using selection sort in ascending order. Show the first 5 pass of the sorting process. So the first pass is, first we will be listing out the questions again, which are 21, 43, 29, 17, 65, 10, and 4. Pass 1. The smallest number is 10, so 10 is swapped out with 21. So that makes the new order starts with 10, 43, 29, 17, 65, 21, and 40. On the second pass, the next smallest number is 17. So we swap 43 with 17. On the third pass, the next smallest number after 17 is 21. So we swap out the positions for 29 with 21. On pass 4, the smallest number is 29. So we swap out 43 with 29. On the final pass, which is pass 5, the smallest number is 40. So we swap 65 with 40. So we got our final answer, which is 10, 17, 21, 29, 40, 43, 65, which is the ascending order. Next question is question 2. Sort data series using merge sort in descending order. Show the steps of sorting process. Alright, so first step, we list out everything in a bracket: 21, 43, 29, 17, 65, 10, 40, which is the original order. We split this in half, which is because we have 7 numbers, so we split into 3 and 4. So we take the first 3 into the first half, which is 21, 43, and 29, and the second half on the right hand side, which is 17, 65, 10, and 40. So on the left hand side, we split the 3 numbers into 1 and 2. So 21, we take that as a first individual number, individual list, and 43 and 29. And then we split again 43 and 29 into 43 and 29. On the right hand side of the tree, 17, 65, 10, and 40. Because there's 4 numbers, we can split in half. So on the first split, which is 2 numbers, which is 17 and 65, and the second split is 10 and 40. So we further split 17 and 65 equally, where we will get 17 and 65 and 10 and 40. So we have successfully isolized all of the numbers. Next is the merging process. So we want to merge this in a descending order. So first we will look at the left hand side of the tree, which is 21, 43, and 29. So we start with the biggest with the tree of 43 and 29. You combine them, so we got our first order, which is 43 and 29. And then next step, we combine 21 with the current list order, which is 43, 29. And because 29 is smaller than 21 is smaller than 29, so it belongs on the rightmost of the list. Step 3, 17 and 65. We look at the right hand side of the tree. We combine 17 and 65 because 65 is bigger, so 65 will come first, and then 17 comes in afterwards. On step 4, we combine 10 and 4, which is from the right hand side of the tree. So that makes 40 bigger than 10, so the list becomes 40 and 10. So we combine the list of 65, 17 and 40 and 10 with the biggest number starting from the biggest number and ending with the lowest one, which makes it 65, 40, 17 and 10. On the left hand side, we have our list of numbers, which is 43, 29 and 21, and on the right hand side we got the list number of 65, 40, 17 and 10. So the result is we combine all of those from left hand side, right hand side according to their biggest to the lowest number, which makes our final answer 65, 43, 40, 29, 17, 21 and 10. Thank you.